In the last episode, the determinant told us whether area or volume survived. Now we ask a more general question. After a matrix transforms space, how many independent directions are still present? That number is the rank. If the plane remains a plane, the rank is 2. If the plane collapses onto a line, the rank is 1. If everything collapses to the origin, the rank is 0. So rank measures the dimension that survives the transformation. The column space is the set of all output vectors a matrix can reach. Why columns? Because multiplying A by X builds a linear combination of the columns of A. Every possible ax is made by choosing coefficients and combining those column directions. So the column space is the span of the columns. Geometrically, it is the reachable part of the output space. Rank is the dimension of the column space. If all reachable outputs lie on a line, the column space has dimension 1, and the rank is 1. If the reachable outputs fill a plane, the rank is 2. If the reachable outputs fill ordinary 3-dimensional space, the rank is 3. The rank does not count how many columns the matrix has. It counts how many genuinely independent output directions those columns create. A column can fail to add a new direction. If a new column already lies in the span of previous columns, then it only points to a place that was already reachable. The column space does not grow. The rank does not increase. This is linear dependence, viewed from the output side. Dependent columns may still change the formula for ax, but they do not expand the geometry of what the matrix can reach. The null space looks at the input side. It is the set of all input vectors that the matrix sends to the 0 vector. These are the directions that disappear completely under the transformation. If a whole line of input vectors lands at 0, then movement along that line is invisible to the output. The null space tells us exactly what information the matrix loses. Column space is about where outputs can go. Null space is about what inputs get erased. Rank becomes especially useful when the matrix is not simply invertible or singular. A transformation from the plane can collapse everything onto a line. A transformation from 3-dimensional space can collapse everything onto a plane. A data matrix can project high-dimensional points into a lower-dimensional feature space. In every case, rank tells how many independent output directions remain. Null space tells which input directions have been lost. Rank and null space are connected by a dimension balance. For a matrix with n input dimensions, each independent input direction does one of 2 things. It contributes to a surviving output direction, or it belongs to the null space and vanishes. The rank counts the surviving directions. The nullity counts the dimensions of the null space. Rank plus nullity equals the input dimension. This is the Rank-Nullity theorem, and geometrically, it is dimension bookkeeping. For a square matrix, full rank means every input dimension survives. There is no non-zero direction that disappears into 0. The column space fills the whole output space. That is exactly the geometric condition for invertibility. If rank is full, every output target has 1 input. If rank is not full, some dimension has collapsed, and the inverse cannot exist. This links rank, column space, null space, determinant, and inverse into one picture. Now the geometry of ax equals b is sharper. A solution exists exactly when the target B lies in the column space of A. If B is outside the column space, no input can reach it. If B is inside, at least one input reaches it. Then the null space decides uniqueness. If the null space contains only 0, the solution is unique. If the null space has directions in it, you can move along those directions and still land on the same B. Here is the core picture to keep. The column space is the set of outputs the matrix can reach. The rank is the dimension of that reachable output space. The null space is the set of input directions that collapse to 0. Rank tells what survives. Null space tells what disappears. For ax equals b, column space decides whether a solution exists, and null space decides whether it is unique. In the next episode, we add measurement to this geometry, dot products, projections, and orthogonality.